consists of coil and conducting wire. So there is something called as psi. Psi is nothing but flux linkages. Flux linkages. So flux linkages are proportional to the current flowing through the inductor. Okay, flux linkages is proportional to the current flowing through the inductor, and psi is equal to L into I. What is L here? Is the proportionality constant, and L is called as inductance of the inductor. Inductance of the inductor. Similar to capacitance of a capacitor, it is the property of the material. Okay, property of the inductor. Inductance is nothing but property of the inductor and is measured in henries. Psi is equal to Li. Psi is nothing but flux linkages. So what is the proportionality constant called? L, which is nothing but inductance of the inductor and is measured in henries. And as again every physical property depends upon area, length, right? Cross section area and length. So this is L is equal to n square mu by mu al by mu a by L. Okay, n square mu naught mu r a by L. What is n? N is nothing but number of turns, right? What is mu? And mu is nothing but permeability. Okay, in capacitance we have seen something called as epsilon. What is epsilon? Epsilon is permittivity and mu is permeability. Okay, inductances you have permeability. Mu naught is again absolute permeability, and mu r is relative permeability. Okay, A is area of cross section, L is length of the inductor. What is the value of mu naught? Anyone? Mu naught is
4 pi into 10 raised to 9.
4 pi into 10 power minus 7. What are the units? Per meter, right? Henry per meter or Henry meter, sorry. Okay. 10 power minus 7, 4 pi into 10 power minus 7. Mu naught is absolute permeability. Mu r is relative permeability.
Henry
Okay.
per meter, right, sir?
Henry. Okay, correct. Henry per meter.
Check the dimension.
No, that's what I'm doing actually. Yeah, it's Henry meter only. Okay. No, it's correct. Henry per meter. I'm sorry. Henry per meter. 4 pi into 10 power minus 7. And square mu a by L. Okay. And voltage current relationship of an inductor. So we have seen flux linkages is L into I, right? So according to Faraday's law of electromagnetic induction, a voltage will be induced only when there are rate of change of flux linkages. Okay, V is equal to d phi by dt. Okay, d into Li by dt. So L di by dt. Instantaneous current I di by dt. V is equal to L di by dt, or V dt is equal to L di, or I is equal to 1 by L integral V dt. Okay. So again from this, any sudden changes in current, okay, any changes in current suddenly or at time 0, which result in infinite voltage, okay, which is not possible, infinite voltage. Hence inductor opposes any sudden changes in current. Okay, inductor opposes any sudden changes in current. Also, if there is no change in current, di by dt is 0, what happens? Voltage is 0. That means there is one V voltage is infinity and the second is voltage is zero, is a short circuit condition. Okay, short circuit condition in the sense, when does this happen? When di by dt is zero. So for DC currents, inductor acts as a short circuit. Inductor acts as a short circuit. Okay. For DC, capacitor acts as an open circuit. For DC, inductor acts as a short circuit. Energy stored in an inductor. Same. Integral P dt, integral V into I, or L di by dt into I dt. So integral or L I di. So L into I square by 2 half L I square is energy stored in an inductor. Half Li square is energy stored in an inductor. Half Cv square is energy stored in an capacitor. Okay. Okay. Summary. If the current through the inductor is constant, that is DC, then voltage across inductor will be zero, and inductor acts as a short circuit to DC. Inductor acts as a short circuit to DC. Next, current through an inductor must be continuous. If not, if the current is discontinuous, then voltage V of t is L di by dt across the inductor will be infinite, which is not possible. Thus, current through the inductor cannot change abruptly. That means inductor opposes sudden changes in current, capacitor opposes sudden changes in voltage. So an ideal inductor never dissipates energy, it only stores, and which is equal to half Li square. Half Li square. Okay. Summarizing, important characteristics of basic elements R, L, and C. V is VIR, V equal to half 1 by C integral I dt plus V t of 0. That's what I'm saying. This is a transient thing. We'll see that for DC. V equal to L di by dt. IV relations. I is V by R, IC dV by dt. 1 by L integral V dt. Okay, power I square R or V square by R. This is a dissipated power. These two are stored energies. Okay. Next series, R equivalent is R1 plus R2. C equivalent is C1, C2 by C1 plus C2. Okay, we haven't seen series and parallel inductors, right? Let me bring those also. Okay, so let me see series inductors. Series inductors. So this is L1, L2, L3 plus minus V1 plus minus V2, V3, and so on. Okay, so we have what is the voltage and current relationship? V is equal to V1 plus V2 plus V3 plus so on and so forth. V1 is L di by dt or di by dt, sorry, L1 plus L2 di by dt. Series current is same, plus L3 di by dt and so on, which is equal to L equivalent di by dt. So L equivalent is L1 plus L2 plus L3 plus so on. So inductors in series are like resistors in series. Okay. Next, parallel inductor. See, these are all basics. That's why I'm going fast. Okay, I can go in depth also, but because this is a short-term course and we are only looking at about HAL and all, so I just want to give you the basics quickly. L1, L2, L3, and this is voltage. So again, I current, what happens? Current divides I equal to I1 plus I2 plus I3 and so on. So this is 1 by L1 integral V dt plus 1 by L2 integral V dt plus 1 by L3 integral V dt and so on. This is equal to 1 by L equivalent integral V dt. So 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus 1 by L3 and so on. Important. Okay. So series inductors, parallel inductors. Okay. Okay. Resistors in parallel, inductors in series. Resistors in parallel, capacitance C1 plus C2, L1, L2 by L1 plus L2. At DC, doesn't change, open circuit and short circuit. Current variable that cannot be changed abruptly. For resistor, it is not applicable. In case of capacitors, it is voltage, inductor, current. Okay, important characteristics of basic elements. Here,
Please.
okay. Yeah, find this. Three capacitors C1, C2, and C3 are connected in series with a 150 volt source. The voltage across C1, C2, and C3 are respectively. Three capacitors C1, C2, and C3 are connected in series with 150 volt source. The voltage across C1, C2, and C3 are respectively dash. Okay, everyone see this? Okay. Yeah, sorry. So not resistors. C1, E2, C3, C1, C2, and C3 in series 60 microfarads, 20 microfarads, and 30 microfarads. Okay, connected in series to a 150 volt source. Okay, so what is the voltage across these three? Okay, how to find this? Anyone?
First, find charge by equating V equal to Q by C. V equal to V1 plus V2 plus V3. And
Yes, find what is the total capacitance C equivalent. Quickly, 60, 30, and 20. 6, 3, and 2 are in series. Capacitors. Capacitors in series are like resistors in parallel, right? So 6, 3, and 2 parallel resistors. What is the equivalent resistance? 60, 30, and 20.
I think it's
60, 30,
10.
and 20. 10, right? 60 and 30 series is 20. 20, 20 is 10. So 10 microfarads. Everyone clear so far? C equivalent is 10 microfarads. What is Q? Q is equal to CV, which is 10 into 150, which is 1500 millicoulombs. Okay, sorry, microcoulombs. Okay, as I told you, in series, what is same? Charge is same. Q is same in series. So what happens to V1? V1 is again Q by C1. V2 is again Q by C2. V3 is Q by C3. Okay. 1500 by 60, 1500 by 20, 1500 by 30. So how
B.
much is this?
25. 25.
25, 75,
50.
50. B. Option B is the answer. Okay, got it?
Okay. Yes.
Okay, now find this. A 50 microfarad capacitor is connected in series with a 150 microfarad capacitor. If the voltage applied to the combination is 40 volts, then the voltage across 50 microfarad capacitor. Voltage across 50 and 150. Similar one. Any answers? Any answers? Option A, B, C, D. Find V1 and V2. Find V1 and V2. Similar
Option
one.
option C.
Option C, right? See directly, if you observe this, you can write something like this. V1 is equal to, sorry, total voltage multiplied by the opposite capacitance divided by total. So how much is this? Sorry. 40, 30 volts. Similarly, V2 is 40 into opposite by total. You will get something 10 volts, right? Directly, voltage division rule is opposite to that of voltage division rule in case of resistors, okay, or similar to that of current division rule in case of resistors. Okay,
Okay.
I don't think these are try to do this. It's a tricky question. Three capacitors C1, C2 and C3 whose values are 10 microfarads, 5 microfarads and 2 microfarads, okay, respectively have breakdown voltages. What is a breakdown voltage? Breakdown voltage means it's a maximum voltage that can be applied to a capacitor before it breakdowns its dielectric material gets disturbed or fails. Okay, when its dielectric fails, that is called breakdown voltage. Okay, so they are having breakdown voltages of 10 volts, 5 volts and 2 volts respectively. For the interconnection, shown, the maximum safe voltage in volts that can be applied across the combination and the corresponding total charge in microcoulombs stored in the effective capacitance across the terminals are respectively. I'll give you a minute, try to solve this. This is a very good question. I'll give you a minute, try to solve this. A, B, C, D option. Any idea? So C1 is given as 10
D.
Am I clear now? Am I audible now?
Yes, yes, yes.
Okay.
Is it D?
We'll see. Okay, I don't think it's D. Okay, C2 and C3. Let's see this combination of C2, C3. What is charge here? See, if 5 volts is applied to C2 and C3, see, if for this parallel combination, can I apply 10 volts?
No.
If I apply 10 volts, what happens to V2 and V3? V2 will
It
be
will.
proportionately 10 into 2 by 7. Okay, which will be more than 5. So it will break down. No, 10 into, let me see, 10 into 20 by 7 is some 2.8, right? And V3 will be 10 minus 2.8. Okay, so it will, C3 will break down. So I can't apply 10 volts. Okay, I can't apply 10 volts to this combination. Okay, so 10 volts is not the answer. Okay, 10 volts I can't apply. So what is the maximum that I can apply? 5 plus 2, 7 volts. Okay, if I can apply 7 volts to the parallel combination, sorry, series combination. Okay, so can you find the charges everywhere? Q1, what is Q1? Q is equal to CV, 10 into 10, 100, 100 microcoulombs, right? 100 microcoulombs. So Q2, what is Q2? 5 into 5, 25 microcoulombs. Q3, 2 into 2, 4 microcoulombs, right? Q3 is 4 microcoulombs.
How is that possible? I mean, like C2 and C3 are in series. So how can we write
Sorry,
different?
correct, correct. So Q2 and Q3 cannot be different, right? They are in series. So Q2 should be equal to Q3. So for that, what you have to do is, you have to find the C23, which is equivalent. Okay, 5 into 2 by 5 plus 2. 5 into 2, 10 by 7 is the equivalent. Okay, C23 is 5 into 2, 10 by 5 plus 2, 7 microfarad. C23 is 10 by 7 microfarads. Okay, so
Adding that to C1 gives effective capacitance.
okay, adding that to C1 gives you effective capacitance, but
And
uh,
and the maximum voltage is 7. So Q equal to C into V.
okay,
So
maximum voltage that I can apply is 7 because C3 may break down, right?
right, right. So we will get 80 if that is the case.
C23 is this much. So what is the okay, C23 is this much. So tell me what is Q23? Q23 can be 10 by 7 into Q is equal to CV,
10.
right?
Yes.
10 microcoulombs, right?
Yes.
So C1 can only have 7 volts. So Q1 can be C is in 10 into voltage can be 7. So this is 70 microcoulombs. Okay.
Yes, sir. The total 80.
Total is Q is 80. Q1 plus Q23 is 70 plus 10, 80 microcoulombs. Okay. And what is total charge in, okay, and effective capacitance?
I think maximum voltage and this charge is only asked in this question.
Okay, the maximum safe voltage in volts that can be applied. Okay, and the charge, correct. So this is C, and voltage that can be applied is 7. Hmm?
Okay, okay.
No, I don't think I can apply 7 volts also. I'm wrong. Sorry. See here. Sorry, this is not the wave. So this right option is not D. Okay, look here, everyone. So we have if I take 7 volts that can be applied to C2 and C3. Okay, and this is C2, C3, which is 5 microfarads and 2 microfarads. So tell me what is V2 and V3? So V2 will be 2 volts, V3 will be 5 volts, right? Right? 7 into 2 by 7, which is 2 volts. 7 into 5 by 7, which is 5 volts, right? Can I apply 5 volts to C3? No, right? I can't apply 5 volts to C3. Okay, I can't apply 5 volts to C3.
Once more, sir. What's that equation about? V2, 72 by 7?
Okay, this, see, you have, if I apply 7 volts to this, okay, 7 volts to this, can you find the voltages V2 and V3 here? Tell me how to find V2.
Oh, okay,
V2
okay.
will
And
be, yeah,
this
V2
opposite.
will be 2 volts, yeah, V3 will be 5 volts, okay?
Okay,
V2
okay,
will be
okay.
5, V2 will be 2 volts and V3 will be 5 volts, which cannot have happen because the maximum voltage that C3 can take is 2 volts. Okay. Okay. So now we have to come this way. So C3 can only take 2 volts and capacitance is 2 microfarads. So Q3 will be 2 into 2, which is 4 microcoulombs. So Q3 should also be equal to Q2 because they are in series. Otherwise, what happens? The voltage will increase. So Q3 is equal to Q2 is equal to 4 microcoulombs. Okay. So the voltage that can apply to 2 or V2 will be V2 is Q2 by C2. Q2 is 4 by C2 is 5. 4 by 5 can be the voltage that is applied. Okay. 0.8 volts. Okay. And now V23 is V23 is 2 plus 0.8, which is 2.8 volts. V23 is 2.8 volts, or the voltage that can totally be applied is 2.8 volts. Voltage can be applied is 2.8 volts only. Now calculating for C1. Now if I calculate for C1, what is Q1? Q1 is C into V, or C1 into V. V is 2.8. C1 is 10 into 2.8 is 28 microcoulombs. Okay. Okay.
Okay.
So what is the total charge? Charge is Q1 plus Q2. Q1 is 28. Q2 is 432 microcoulombs is the total charge. This is total charge and this is voltage. 2.8 and 32. Option C. Okay, it's a tricky question. That's why I told you to understand it. Clear, right? Shall I repeat? Is it clear or shall I repeat? Clear, na?
Clear, sir. Clear, sir. Very good question.
Yeah. Yeah. Okay. Okay. Find this one. For the circuit shown in the figure, the capacitance measured between B and Y terminals. Capacitance measured between B and Y terminals. Find the capacitance measured between B and Y terminals. Everyone. Option A, B, C, D. No answer? Okay. So
Sir, I
everyone to
think
your screen. What happened?
CS plus CC whole divided by 2 is there is no such option. I just got like that.
Okay. Okay.
I don't
So look
know.
at this. Okay. Look at the screen, everyone. See, what is the different definition of parallel circuits? As I told you, how do you call two elements in parallel? When do you call two elements in parallel? In the very first class, I told you. When can you call two elements in parallel?
When we apply current, it will split.
No, no, no. Even in
The
star
both
delta,
ends.
it gets
Okay,
splitted, right?
both ends.
Yeah. And both ends of one element connected to both the ends of other element, then you can call them an parallel. Okay, when both the elements of one element are connected to both the ends of other element. Can you see any parallel combinations here? Any parallel combinations? See this R and Y. This one. Y and G. Call it. How are these two? Anyone? Parallel, right? Directly connected. These two are connected. These two are connected.
Yes,
Are you able to see it?
yes, yes.
Similarly, this one and this one. Similarly, this one and this one. See, I'm redrawing it. You can redraw it like this. CC. This is terminal B and this is terminal Y. This is the ground. Okay, this is CS. This is CC. Or this is CC and CS. Again, CS, CC. Now, can you say what is the answer? Now, find the capacitance between B and Y terminal. Understood how I draw this? How I drew this? From this one, both are equal, right? CC parallel with CS. It's CC plus CS by 2. Sorry, CC plus CS. It is CC plus CS. Here also it's CC plus CS. Okay, and those two are in series. Okay, this is how the circuit becomes. This is my CC. This is CC plus CS. This is again CC plus CS. This is P and Y. Now these two are in series. Okay, capacitors in series are like resistors in parallel. Equal capacitors in series. It is CC by CC plus CS by 2. CC plus CS by 2 in series in parallel with CC. So what is the capacitance? Equivalent capacitance? CC plus
C,
CC.
C stands
D.
CC.
It is 3CC plus CS by 2. Okay, clear?
I had done a grave mistake. Like just took it as like some kind of reactance and like or Wheatstone bridge, that kind of thing I have done.
Okay,
CC by
okay.
CC
I
equal to
understood.
CS.
Even if that's a Wheatstone bridge, you have a short circuit here, right? That's why I thought people will usually think this is as a Wheatstone bridge.
I have
And
done
again,
that.
what happened?
I have done the same mistake.
Yeah, yeah, I know. Okay. Is it clear now?
Please, please.
Yeah. Okay. So it's a very simple problem and people tends to get confused. Okay. So similarly, these problems, okay, these numericals, simple numericals, try to do this, find the equivalent capacitance.
The left side is not clear. Is it 20 microfarad?
Yeah, it's 20 microfarads. See quickly, 25 is 4, right? 20 into 5, 100 by 25 is 4. Okay, 4 and 6 is 10. 10 and 20 is 20 by 3. Sorry, 10 and 20 is 30. 30 and 60 is again 20 microfarads directly. Okay. Okay. Following me? Yeah. 120 and 60. What is the equivalent? 120 and 60. 120 by 3 is 40. 40 and 20 again in parallel is 60. Okay. 60 and this is 120 again. 60 and 120 is 40 microfarads. Direct questions, okay? Direct questions.
Okay.
Now tell me this one. Direct one, sorry. This one. What's the answer? Wheatstone bridge. Remember, this is a Wheatstone bridge. All the branches are equal at C directly. Okay.
Okay.
I can remove this series parallel. Oh, you can short it or remove it. You'll get the answer as C. Okay, Wheatstone bridge.
Okay.
Okay. Next, this one. Quickly. 12 and 4. 12, 4 is 3. 3, 3 is 6. 6, 6 is 3. 3 and 2 is 5. 5 and 5 is 2.5 microfarads. I'm giving you these many because see, when we are habituated for resistors, people tend to get confused with capacitor. That is why it's very simple, but sometimes in case of series parallel combinations, you may do mistakes. Okay, understood? It's 2.5 microfarads.
Yes,
Series
yes.
parallel parallel series. Clear?
Clear, clear.
This one, quickly. CC is C by 2, C by 2 and C. 3C by 2, right? 3C by 2 and C in parallel. 3C by 2 and C.
3 by 5.
Or like, hmm?
3 by 5 C by 2. 1 by 3 by 2 plus 1. 3 by 5.
Okay, 5C by. Not, it's 5 by 3, right? Oh, sorry, 3 by 5, correct. 3 by 5. 3 by 5
Yep.
plus C. 3C by 5 plus C. 8C by 5. Okay, 8C by 5. Clear so far?
Clear, clear.
So similarly, inductance. Quickly. You can tell me the answers for inductance.
First one is 7.
Hmm?
7 first one.
Yes, first one is 7, correct?
Second one 3.
Hmm. Okay, do the last one. So this is simple. 4. I'm sorry. 4 and 4 is 2. 2 plus 1, 3. 3 and 6 is 2. 2 and 5 is 7. 7 Henries is the total. Here again. 4 and 2, 6. 6 and 6 is 3. 3 and 1 is 4. 4 and 12 is 3. 3 Henries. 60, 20, 30. Directly 10 millihenry, right? 632 is 1. 60, 30, 20 is 10. Always. Okay? 10 and 25, 35 parallel with 10. It is 350 by 45. 350 by 45. Okay, L equivalent. Now coming to the last one. Tell me how to do this series, parallel, parallel, series, any?
12 and
Do
4
you
is
see?
parallel.
12
12
and
and
4
4
are parallel. Yeah,
and
and?
3 and 2 and 6.
Hmm.
Every
Right? You are
every
able to see this, right? 3, 2, 6 or 6, 3, 2 is directly 6, 3, 2. Similar to 60, 30, 20. 1. 12
okay.
and 4, 3. Right? 1 plus 3, 4. 4 parallel with 1. No, not 4 parallel with 1. Not. Yes, 4 parallel with 1. Correct. This is 3. This is 1 and this is 1. 4 parallel with 1. 4 by 5. 4 by 500. Okay, clear?
Clear.
Next, there is a small concept called principle of duality. Duality principle. Okay, the duality principle asserts a parallelism between pairs of characterizing equations and theorems of electric circuits. Okay, two circuits are said to be duals of one another if they are described by the same characterizing equations with dual quantities interchanged. Okay, see, we'll see some of the advantages of duality in the next classes also. Simply, there are dual pairs. First, we'll see duality is nothing but you can interchange one circuit to another circuit with what you call pair of characterizing equations and theorems. Okay, there is a parallelism between two circuits. Okay, or two pairs of characterizing equations or theorems or elements. Okay, so first we'll identify what are dual pairs. Okay, so for resistance, it's conductance G, inductance, capacitance. Okay, tell me, resistance, it's conductance. Okay, inductance, it is capacitance. Okay, resistivity, it is conductivity. Okay, rho, it's sigma. And in what else? Nodal analysis, mesh analysis, KCL, KVL. Okay, and what else can you say? Thevenin's, Norton's, Thevenin's theorem, it's Norton's, yeah. Voltage, current, voltage source, current source, node, mesh, series path, parallel path, open circuit by short circuit, KCL, KVL, Thevenin's, Norton's, star by delta and delta by star, R into I dt is G into V dt, nothing but replace R with the G, okay, I with V, okay, voltage, it's current, L di by dt, replace L with C, I with voltage, C dV by dt. Okay, 1 by C integral I dt is 1 by L integral V dt. Can you tell me some more? Some more dual pairs? Open circuit, short circuit, series, parallel, right? Star, delta, okay. There's something like this. You can convert a voltage source, yeah, current, practical voltage source to a current source, and so on, similar to that of Thevenin's and Norton's. Okay. Next, construction of a dual of a network. If if you are given a network and if you want to find the dual of that network, okay, how to do it? Okay, the advantages and applications we'll see in the coming classes. Constructing a dual of a network. Place a node at the center of each mesh of the given circuit. Okay, place a node in the center of each mesh of a given circuit. Place the reference node outside the dual circuit. Okay, outside the dual circuit. Draw the lines between the nodes such that each line crosses an element. Okay, replace that element by its dual. Okay, to determine the polarity of voltage source and the direction of current sources, this is important. To determine the polarity of voltage source and direction of current source, follow this rule. A voltage source that produces a positive or a clockwise mesh current has its dual current source whose reference direction is from ground to the non-reference node. This is important. To determine the polarity of a voltage source and direction of a current source, follow this rule. A voltage source that produces a positive or a clockwise mesh current has its dual current source whose reference direction is from reference or ground node to the non-reference node. Ground node to the non-reference node. Okay. If this is a voltage source, if it produces a clockwise current, this will have a ground to non-reference node direction of current. Okay, I'll show you how to construct a dual of this network. Everyone, see here what you have to do. First step, place a node at the center of each mesh and place a reference node out of the outside the given circuit. Each mesh, there are two meshes. I place two nodes. I'll call them as 1 and 2, and a reference node outside. Okay. Next, what you have to do, draw lines between the nodes such that each line crosses an element. Replace that element by its dual. Okay. So in this mesh 2, I have to draw 1 to the reference node and 2 to the reference node lines such that each line crosses an element. So I have a voltage source here. It crosses something like this. I have a resistance here. It crosses something like this. Okay. And from 1 to 2 also, you have to draw it. Okay. And 2 to reference node again. 2 to reference node. Now what you have to do, you have to replace all these elements with their duals. So in drawing this is my node 1. This is,
Like, repeat the second thing more.
yeah. Draw the lines between nodes such that each line crosses an element. Replace that element by its dual. So between all the nodes 1 and 2, there is one node. I have to replace it with this dual. I have to draw the lines. I'm drawing with dotted lines. 1 to the reference node. All the elements. I have one element here, the other element through this. Similarly, through this. Okay. Let me draw it. It will be clear to you. Okay, this is my reference node. Okay. So between 1 and 2, there is an inductance. So this will be replaced by a capacitor. Okay. Capacitor. Okay, between 1 and 2. So 1 in reference node, what all we have? A voltage source and a resistor. R1 will be replaced by its dual. What is its dual? G1 or 1 by R1. So this will be G1. And what is this voltage source becomes? What is the dual of a voltage source? It's a current source. So this is producing a positive mesh current or a clockwise mesh current. So this should be from reference node to the non-reference node. So this will be I. Okay. Similarly, at node 2, what happens? I have a resistor R2 between node 2 and reference node. So this will become G2 and a capacitance which will become L. Okay, clear? This is dual of this network.
Okay, so if the voltage source was in reverse polarity, then the current also changes.
Yes, current also changes.
Okay, okay. Just opposite direction, right?
Opposite direction. You can remember this way. If this is positive, this will be the direction. The direction will be always uh, outside from the positive terminal. Okay.
Okay, okay.
Yeah. I draw the dual for this network. Try to draw the dual for this.
I haven't taken the pen and paper for that, but I will try.
Okay. So let me show you. This is how you do it. You will have 1, 2, and a reference node. Okay. This is 1, 2, and a reference node. So what happens from 1 to reference node? There is a current source. So you'll have a voltage source of value 50 millivolts. Okay. From 1 and 2, there are two elements and they are in series. Now they will be in parallel. A resistance or a conductance of value 1 by 10 mho. Oh, sorry, 1 by 10 mho. I'm sorry, 10 mho or 1 by 10 ohms. Okay, 10 mho. And this will become an inductance of 3 Henry. And this will become a capacitance of 4 farads. Okay. See, the concept of duality helps us in finding, see, some circuits it's better to use Thevenin's theorem. Some circuit it's better to use Norton's theorem. That's the simplest way to tell. If I want some, if you remember, there is a question like something like this.
So one doubt in
Yeah.
between, so that
Hmm?
one doubt in between, that 50 milliampere is the current source, right? So
Hmm.
direction is from down to up, but the voltage source should be in opposite direction, right, sir?
No, no, this one. I told you, right? If this is positive, this will be the current direction. See, if this voltage source is producing a positive or a clockwise mesh current, what happens? It is from the reference node. The current will be from reference node to the non-reference node. The direction will always be from this.
So
Okay. Yeah.
I thought it's like a dual circuit, so everything will be opposite, that kind of thing.
No, it's not opposite. It's not opposite.
Okay, okay.
Hmm?
So
Yeah.
elements are actually
No,
like that.
duality is not opposite. Duality is not opposite. Okay. Remember, duality is not opposite. So that's what, if you see some circuits, you'll get very easy answers because some circuits are confusing. What you call, I'll particularly bring out this example. So this is a 10 amp source. Okay. See this you'll get, I think, much of clarity. 10 and 30, 20 and 20. Okay, what is Norton's current? Find the Norton's equivalent current source for this between terminals A and B. What is Norton's equivalent current? Can you find it? We have done a similar, I don't remember the numericals. It's a similar one. I thought people will ask me there, but anyhow, tell me what is Norton's equivalent current, IAB? First of all, how do you find the Norton's equivalent current? How do you find the Norton's equivalent current?
Short circuit AB terminal.
Short circuit AB. Okay, this is IN, right? So now tell me what is IN? So how to find IN at least?
Both are parallel resistance. So
Hmm. Calculate it and tell me. I think we have done the same problem, right? Somewhere previously. So able to see it, right? This one, this particular one, not this one. Sorry. This particular one. Tell me what is Norton's equivalent current? IN. See, this is how I did. If you remember, what I did, I found V Thevenin and then I converted it into IN. Okay, it's difficult to understand and how find IN directly here. IN is not same as 8, right? Okay, this is what IN. So it's always better to find the dual of the network sometimes and do the solution. Okay, understood how can, like, where can you apply in duality principle? It's an example. Even we'll see in case of transients also, it's always easier to apply duality. We'll see directly. We'll do some problems, and I'll show you how to do it with the help of duality principle. Okay, this I think you got an idea how to find IN now. You always have to do this. This is the best way to do this. Find VThevenin and then convert it into IN. Okay.
Okay.
Understood it, right? Any clarifications needed?
But still,
Hmm.
any other, there should have been any other method, right, sir?
Yeah,
Like,
there is one more method. Try to
parallel,
solve it this way.
like
Yeah,
two
for the
parallel.
hmm.
So, finding the current in each branch and the 8 minus the rest should give the other.
Try to do that. No, it's not that simple, right? See, if for example, if you say there is some current flowing here, say X, and there is some current Y is flowing. So can you tell me which is IN? 8 minus X or 8 minus Y? X plus Y is 8, right? So 8
Uh,
minus X or 8 minus Y. You can't say it that way.
okay.
Hmm. You have to find current through 10 ohms resistor. You have to find current through 20 ohms, 50 and 40. Then you'll get it. Anyhow. Okay, even then, see, if this is X and Y, this is A and B, you'll again get A plus B is 8, X plus Y is 8, right? Are you getting me? Am I making it more complicated? See, if
Uh,
some problem is given like this in your exam to find IN, directly IN, don't try to attempt directly. You'll definitely get confused. Better to find the VThevenin then do this, or you can find the dual of this network and find the voltage between A and B terminals, and then you'll get or like voltage and resistance, voltage dual of the circuit and voltage, that is nothing but your IN. Okay.
okay.
Try to do the same problem with the dual of this. Okay. Take a screenshot and try to solve it using the duality principle and find voltage VAB after converting it to the dual. Okay.
Okay.
Yeah.
So here,
Hmm.
here there are three mesh. No.
Okay. Yeah, you can try different ways. That will give you more clarity, I'm sure. So try to do that in whatever way you find it better. Okay.
Okay.
Yeah. So I'm ending the class for now. And the next class we'll see the transients. Okay.
Okay. Thank you. Thanks.